for awesome. Great. So Snorkel. Serena, do you want to refresh us on what Snorkel is?
Yeah, sure. So it's kind of like, it's like a method to label like a bunch of data pretty efficiently. And the way to do that is to use like weak supervision, which is to get a bunch of sources of like labels, I guess, that are like not super accurate, but they cover like a large amount of data. So it's like the concept of labeling functions, and they're just like little snippets of Python code. And then Snorkel just kind of uses those labeling functions, tries to find out which labeling functions are more accurate than others, and then uses it to like predict what labels like fit to data with a bunch of different models as well.
Exactly. Cool. That's exactly it. That is exactly what Snorkel is doing. It's a weak supervision technique which uses a concept which the researchers developed called data programming, which is basically just creating those labeling functions that Srita mentioned, which basically, even though they might not do as well as a human labeler, they'll be much faster and more efficient at labeling lots and lots of unlabeled data, which, as the researchers talked about in the paper, helps get the same level of modeling performance as if a human laborer were to do it for a long time. Like what you can do in hours with Snorkel to get the same performance would take sort of months with a human laborer. So that's sort of the motivation behind Snorkel. So how does it actually work mathematically? Let's see if we can get a better understanding of that. So on a very high level, before I go into that, who did anyone have a chance to see all these videos? Serena, did you see all of them? Cool. I don't think anyone here knows what Gibbs sampling is, except Serena. Let's just watch the video. But who knows what maximum likelihood estimation is, along with discrete marginal probability distributions? Anyone? And if you don't, that's totally cool.
Nate. I know a little bit about like, MLE and like some of that stuff, but not
cool.
Discrete.
Yeah, I saw you took linear models, correct?
Yeah.
Right. Okay. Yeah, we don't have to get very into the nitty-gritty of it, but I'll just reference it today and I'll briefly touch on it, the concepts which are important for understanding this. If you guys take higher level stats classes, you will come across these, like probability, for example. But if you're a pure CS, then probably not. But still, it's kind of cool if you're interested in ML, because you do come across these things. Okay, and I'll do that as we go along. So on a very high level, if we have n unlabeled data points and our subject matter experts or SMEs think of n human-generated labeling functions, our goal is to label those unlabeled data points as best as we can without having access to any ground truth labels. And in this sort of tutorial or discussion, this vector y will refer to the actual ground truth labels. And just a quick thing, you guys can interrupt me at any time during this tutorial if you have any questions or comments on anything. Like I know that this stuff, it looks pretty complicated. Even the terminology can be complicated. So please stop and ask questions to not just me, honestly, everyone else can participate in answering them too if you want to. So we have m unlabeled data points, n human-generated labeling functions, and we don't have access to any ground truth. How do we label these unlabeled data points? So basically, the first thing we need to do is we need to create a label matrix, which is basically the output of all the labeling functions for all the training data. So its length is the length of the training data, m by the number of labeling functions, n. So it's an m by n matrix. And we input that matrix into what we call a generative model, which Srina read about a little bit for last time, and she had questions on. So hopefully we'll get much more into it today. And that generative model returns a vector of probabilistic labels, which in this tutorial, as some of you read, we're gonna assume that we have 2 labels for each data point. So it's a binary sort of classification problem. So these probabilistic labels are the probability that that data point belongs to whatever we assign as the positive class. And so they range from 0 to 1, as we'll soon see. And then, because we want to reduce noise in the labeling functions, we throw those labels into another discriminative model, which basically just generalizes better. I'll talk about that more at the bottom. So yeah, like I've said here, that's a lot. And I think it'd be most helpful if we sort of break it down piece by piece. So let's start with our label matrix. And again, please interrupt me at any time or raise your hand if you want to ask a question. And I'll pause to make sure that people have the chance to ask questions too. So as I said earlier, our label matrix lambda, big lambda, is an m by n matrix where we represent the output of our n labeling functions on our m unlabeled training example. So it's m by n. And as I said, our problem is binary classification. So the elements of lambda can be one of three things. A 1 if it's the positive class which we've assigned, -1 if it's the other class, or 0, which essentially means that the labeling function abstained from voting. It was not sure enough to give a positive or negative label, so it abstained and just said, I'm not going to label this. And this notation is for the empty set, which basically just means empty, so nothing. So more formally, we have lambda is in -1 or 1 with the union of the empty set, and it's m by n. This terminology might have scared some people or maybe made you curious a little bit about what it actually means and looked a little scary, but that's all it means. It's saying every element in lambda is either a -1 or a 1, or it's an empty set, and lambda is an m by n matrix. So now we're going to use lambda for our generative model.
Quick question.
Yes, Nate.
So maybe I missed this, but is the label matrix, like, is that just supposed to come from like a subset of like already labeled data that we have, like a subset of our data set, or
no?
Where does that come from?
This label matrix comes from, we have m unlabeled data points, right?
Yeah.
We're going to pass each of them into all of the labeling functions we have. We have n of them.
Right.
Then
Okay.
we're going to have the output of all of them. So the columns represent the labeling functions. So this is 1, 1. So this is labeling functions 1's label on our first data point, and then labeling function 1 on the second, third, fourth, so on, and then labeling function 2 on 1, 2 on 2, 2 on 3, and so on and so forth. Does that make sense?
Yeah.
Cool.
Thanks.
Awesome. Any other questions so far?
Wait, I have a question for like the more general case of lambda, like with that funny notation thing. Then like in the array sort of thing, on like the left side of the union, there'd be more numbers, and then it would always be union with the empty set.
One more time, Serena.
So like I understand the notation, like the funny notation for this example, but I'm just wondering in the more general sense, like when this is generalized, then within the 2 square brackets, it would be like the list of possible labels, and it would always
Exactly.
be the empty set.
Yes.
Okay,
Yes.
got it.
But I haven't actually thought about the non-binary case yet, but I think actually what we do instead is if we have, say, m labels, we just do this process m times. And we'd say it's either like, we do it for all combinations of our labels. Yeah. So I think this lambda would be 2 for the whole time, but we do the entire process like every single time for every single combination of our labels, of our pairwise combination of labels. Does that sort of clear it up? I think. I'm not actually sure on that, but that's what I'd guess.
Okay, so the guess is that like the thing, like the array, I don't know, like what is the technical term? Is it like a set on the left side?
Yes.
That like it will only have 2 elements in it is like your assumption right now.
Yes, that's what I'm assuming for the tutorial. And you asked a great question, which is if we had more than 2 classes which the data can be labeled at, we would probably repeat the entire process for all sort of the pairwise combinations of labels. So if we had 3, we'd do 1 and 2, 1 and 3, and 2 and 3. And for each of those 3 types, we would set one of them as 1 and one of them as -1, and then just repeat everything down here. And then find a way to aggregate all of them. And that's how it's also sort of done with multi-class classification using sort of like a loss function like cross entropy. You sort of consider all those pairwise combinations and sum them all up to get your final loss. with sort of similar framework here. If that didn't make any sense to you, that's cool if you never looked at cross entropy, but that's kind of, that's the way I guess it's done. Anyone here looked at cross entropy? Nate, Carson, I'm sure you have with your neural nets. Yeah.
Like the loss function? Yeah.
Exactly, yeah.
Yeah.
All right, cool. Any other questions? Carson, Marwan? Awesome, all right. Now we move on to our generative model. Carson, yeah?
Yeah, so I'm just confused, like, when it would ever, like, label it as no label.
I think we would have to put that into our labeling function. So our labeling function is a Python script, as the authors talk about. Let me go to that. Like this, for example. And my guess is either we could say a case like an if statement in this function where we'd say, if nothing else, if it's something else, or maybe an else, if it's not one of these statements, then we'd abstain from voting, or we'd just say, yeah, that's exactly what we'd say. If the conditions, if the conditions don't match, like say our data is super funky and we can't really determine, for example, these sorts of things, whatever is in our labeling function, the heuristics, my guess is we'd sort of encode like some more code in there to say like, if those conditions don't match, then abstain. Or it might, or what's the way the pipeline might be set up is that Snorkel might just automatically do that. If it doesn't really return anything here, then don't label it as anything. It's probably in the Snorkel pipeline somewhere, but not in the user-defined labeling functions. Good question. Did that make sense?
Yeah, thank you.
Cool. And obvious, again, I'm purely guessing here. I don't actually know. They didn't really talk about it in the paper. They didn't do a very good job organizing everything, I would say. I've read papers which are much better organized, but doing the best we can here. All right, let's move on to our generative model. So as I mentioned above, the objective of our generative model is to return a vector of probabilistic labels y hat of length m for each of our data points, where each y sub I hat is between 0 and 1, and it represents the probability of belonging to the, excuse me, that should say positive, I'm sorry. Let me change that. Whatever we say is the positive class. Remember, this is a binary classification problem. And in the paper, the authors talk about needing 3 pieces of information to encode sort of this generative model. We need to model the propensity of each labeling function, or how likely it is that it returns an actual label and does not abstain. That's one. Number 2, we need to encode the assumption that the LFs are independent from one another. And since this is probably not the case, we need to encode the dependencies or correlations between them. And we'll go into how that's actually done. But modeling the first 2 are fairly straightforward, as we see, because we don't need really ground truth to do that. But things sort of get trickier for dependencies, because you might think that they do need ground truth, but we don't have them. And a variable which we don't have access to, but we need is called a latent variable. Any questions?
I'm confused as to like what this like encoding information is. Like, what is the purpose of it?
It's for our model so that we have this information for when we're actually doing the labels, because this is empirically what the authors of Snorkel found was the greatest pieces of information to need in terms of getting the best performance.
So is this like something like a parameter you need for a generative model, or like how does it relate to the model?
We're going to put these as vectors into the model. So this is, as you read last week, this is the full model, and this vector right over here represents the subvectors of each of those cases, so dependencies, independence, and propensity. And basically, we weight each of them here with this weight vector.
Oh, I see.
Yeah, and that is
Okay.
this is all directly taken from the paper, by the way. This is exactly what they say. Yeah, the annoying part is you never really can figure out like what was the intuition behind why they chose this formula specifically. But basically, it's just we want to encode all these things, and then we want to weight them by importance based on our data, which is kind of how all machine learning works, right? You have some input data and you get weights for whatever model you're choosing, and those weights are kind of based on your data. So you want to have good data. But this is a little bit unique because this is unlabeled data, which we don't even have ground truth for. So, all right, let's talk about how we get those dependencies, or excuse me, information. Yeah, Nate.
All right, I have one more question too.
Yeah.
I have a question about number 2 and 3 on those three key pieces. Unless I'm just reading this wrong, aren't 2 and 3 kind of contradictory to each other?
Exactly.
Like if we, okay.
That's right, but we want to kind of include both of them in sort of our final model, which is, I guess that's what the creators of Snorkel found was best empirically. They don't actually say why we have both of these.
Okay.
I guess it led to the best performance when we first treat them as independent and then we find those dependencies.
Right. Okay.
Yeah, great questions, you guys. All right, so let's start with propensity. So again, propensity is how likely it is that the LF returns an actual label and not does not abstain. So for the propensity, for a data point, for an entry in the label matrix, we can represent it with a 0 and a 1, where we have 1 if the entry does not abstain, it has a label, or a 0 if it did abstain. So for data point I and labeling function j, phi label I of sub j, given your label matrix and your ground truth labels, is 1 when your entry of the label matrix ij is not abstained, basically, is not that empty set. So you might be wondering, why does this accept the ground truth labels when we said we don't need them and we don't have them? That's just how they put it. I think they just wanted to be consistent, so they just wanted to make all of them the same. But in reality, only this one doesn't really need y at all, as you can see. So tomorrow, let's go to independence. Or did anyone have any questions on propensity? Cool. Let's go to independence. So again, the way the authors said we treat the LFs as independent is basically obtaining the accuracy of each labeling function, which is basically comparing it to the actual to the ground truth. So hopefully that causes some confusion, like I've said down here. Up here, we've said that we need ground truth, but we don't actually have it. So how do we kind of solve for this? And we'll talk about that as we talk about the actual model. It comes from right here when we're using the negative log marginal likelihood, which basically means we're trying all possible combinations that ground truth can be. So just keep that in the back of your mind for now, but this is how they've defined measuring accuracy for an entry ij in the label matrix. If the label is the correct label, then it lights up. Oh yeah, I'm sorry, I forgot to mention, this notation here is the indicator function. Has anyone here been exposed to that? Basically, for CS people, it's a Boolean variable. If the condition is true, it's true, and if not, it returns false, which in our case, we're modeling as 0s and 1s. Which is why our vectors, our entries are 0s and 1s, our entries which are going to become vectors when we combine them all together. All right, so that's independence. Any questions? Awesome. So now let's get into the fun stuff, which is dependencies. So as we saw here, excuse me, we don't have ground truth, as we know, and that's the biggest challenge to our problem. As we'll soon see for independence, we can simulate ground truth by looking at all possible combinations of sort of the ground truth labels. But That does not really work for dependencies because it's very long to calculate. Sorry, first I'll talk about our dependency function or correlation function. So we have for data point I and labeling functions j and k, taking in the label matrix, our ground truth labels, we return a 1 if the entry of ij in the label matrix is equal to the entry ik for all jk's in C. And these are two labeling functions. So basically, for all of the pairs of our labeling functions, we're going to be looking that we decide are correlated, and we'll get to that in a moment. We're going to say that those pairs are correlated if the entries are equal to each other. So this is purely based on our empirical data set from our label functions. So C over here is all the pairs of labeling functions which we have chosen to assume are correlated. Now, how do we choose which ones? This I still don't understand completely, but I'll talk about it a little bit what I have found out, which is in one of their earlier papers, which I'll talk about. So you might be wondering, why don't we just test if all of them are correlated? But that would become very, very fast. Or excuse me, that would take way too long. And if we have lots of labeling functions, we'd have sort of 2 to the n combinations to try out. So that'd be very computationally expensive. So instead, the authors proposed this method. So it's all of this right here, and I'm going to try my best. I do not understand this fully yet, so I will try my best to kind of make it as clear as I can. So as you'll see, I mentioned the general model over here. That is very similar to what they've done here, except now they've added these two sorts of sums. And as you can see, T is the set of dependency types of interests, and S sub T is the set of index tuples indicating the labeling functions that participate in each dependency of type T in big T. And so you might be wondering, what is a dependency type of interest? One of the ones is correlation, which is the one we'll be looking at right now. And you can also have this sort of conjunction, which is defined like this. But we're just going to look at correlation. So we've looked at this. This is the exact same thing as this right over here. And so basically, for every sort of possible pairing of labeling functions in correlation, which is basically all the possible pairwise combinations of labeling functions, we're going to follow this model right over here. And that's our full model, which we have here. And basically what we're going to do is, because, like I just mentioned, trying all combinations takes a very long time. If we were to do it like this and put it in like this and put it into the model here. Instead, what the authors propose, now I don't know how they came up with this. They don't mention how they came up with it. They say we can optimize a different objective, which is the log marginal pseudo likelihood, which is a mouthful, which quite frankly, I don't know why they called it the pseudo likelihood, but that's what they've decided to call it. So basically what we're doing is, this is our final function to optimize right here. Basically, it's outputting a single labeling function conditioned on the outputs of the others. And we're using L1 regularization to induce sparsity, which basically takes some of our weights down to 0. How they came up with this, I have no idea, but that's the method which they say works best. So this is what we're modeling right here. Take a second and look at all this and ask questions.
So, okay, I still don't completely understand
Yeah,
that equation,
yeah.
but it kind of looks like cross entropy, right?
Sort of,
Like
yeah.
like argument of negative of the log of something.
Yes, so this M represents all of our data. So for all of our data, we're going to sum the log of all of the possible values for ground truth.
So all the labels.
This function is right here, and that's given the labels for whatever labeling function we're doing, looking at. We're looking at all the other labels which are not that labeling function, and we're modeling the probability of these two things right here, and then we're adding a regularization term.
Okay.
Where
So one more time, there's the two things in there. You know, I understand on the right, that's all the labeling. That's like the labeling matrix except for like without J, right?
Exactly.
Or without labeling function J
Exactly.
for any given
Yes.
example I.
Yep.
So using that as our like prior, or like as the conditional, we're looking at the probability that the label matrix matches with yi.
Exactly.
I don't know how to interpret that last part. Okay.
Yeah. So this means for these yi's, we're testing out all the possible vectors yi, or excuse me, yi is not a vector. Yi is a simple label. So basically, for all the possible labels, we're testing it out in this function right over here.
Okay.
And the correlation function also does not really require yi. So one thing that confused me is, why does this correlation function accept yi? Why does it need to when it doesn't really use it? Like here it is, it doesn't use it over here. It's just using another element in the label matrix. So some of the things in here confused me. That was one of them, like why they even mentioned it. My guess is they just wanted to keep it consistent with independence in terms of the parameters. But I don't think that's really that important. Carson, Marwa, and Serena.
I'm kind of confused about the part at the end of that like function you were just showing us. I forgot what you called it.
Is it the indicator?
The part with epsilon.
Oh, here?
Yeah, that part.
So this is the L1 regularization term. Who here knows what regularization is for machine learning? Me?
We went over that in 158, but I
Got you.
I forgot.
So the purpose of regularization in ML is to reduce variance or overfitting. And basically, let me actually, regularization ML. This is cool. We can learn these concepts. Regularization ML. So let me go to a towards data science article, if it won't give me a paywall. So, whoops, sorry. So let's see, where can I go? All right, I'll just go to Google Images. Okay, this is not going to help. So actually, I'll just explain it. Sorry. So basically, are you familiar, Carson, in ML, how we can overfit on the training data?
Yeah.
So regularization is basically a way to prevent that. We have sort of a loss function, which is conditioned on our weights. And basically, we try to minimize that loss function and find the weights that minimize that loss function. But oftentimes what happens is we're training our model on the training data set, but that might lead to overfitting. So basically, we add sort of this term right here, where theta is our weights, and this epsilon, excuse me, is an arbitrary number, scalar, which we determine by hyperparameter tuning and grid search and all those things, which we won't get into right now, which basically serves the purpose of shrinking weights down lower. So basically reducing their magnitude. Because when we reduce their magnitude, we reduce sort of their influence on predicting our outcome variable. And basically, when we have weights that are developed using the training data set, many times our weights are very, very high and thus are overfitting. So we use this term to sort of reduce the value of those weights. And that is basically what regularization is. Nate, do you want to add to that or clear it up if I was confusing at all?
No, that seems like it's right. Like it kind of like dampening on like how much we change our parameters by, right? Which like in neural nets is like, you know, the weights.
Exactly.
But yeah.
Basically, we're just reducing the magnitude of our weights so that we can generalize better to new data. Because usually what happens is we overfit on our training data set when getting a model. So to generalize more, we introduce this sort of term to what they say is induced sparsity, which basically means shrinking weights to zero. And what, as we'll soon see, this epsilon term actually serves two purposes in this problem, but in general in ML, what I've said earlier is what it's supposed to do, is shrink those weights down. Marwan, Serena, did you want to add anything or ask anything?
Yeah, I was just gonna ask about the general model. I'm still having a hard time understanding the definition, specifically like what S sub t is, and like sort of what we're like what's being expressed here.
Right. So this is very, very general. This T is basically a set of the dependency types of interests, which could be correlation, which could be conjunction. As they've said here, we're only going to consider correlation as the authors have defined here, along with accuracy and lab, but we already know how to calculate those two, so we don't really have to worry about it here. And they also don't really, they seem to have fixed it. This paper was from 2017, and the one which Brian assigned us was from 2019. So it seems like in those 2 years they did more R&D and they shortened it to basically take this away. They do talk about in this paper though using this method just for correlation. So basically T is just 1 because we just have one dependency type right here, which is correlation. And then S sub T is all the possible combinations of J and K is all it is. And then for all of those, we have weights and we have a function like this, which is defined like that.
So, so what this really does is like we're summing across like any possible type of like dependency measurement or like heuristic, like this correlation or dependence, independence, like that's what T is. And then S of T is just like do this for every possible combination of labeling functions.
Exactly, JK.
Okay.
Yeah, great question. And so they say that we need to minimize this term right here. We need to find the weights, which is what this terminology means. Argument is basically the minimum, the value of theta, which is our weight vector, which minimizes this term right here, is all this is saying. Now this term is pretty complex, but when you really boil it down, it's just for every single data point, since we have m data points, find for all combinations, for all possible labels, find this with this regularization term added onto it. And so basically, as you can imagine, and as we talked about, this takes a very long time, especially trying all these combinations out and these sorts of different things. And like I said here, that's why we can't really use, we can't really just treat everything in ST in C, because I think the reason is here the math is a little bit more complex than here, because we have these extra pieces of information to encode into the model. But here, when we're just looking at correlation, we can use the marginal pseudo likelihood, which again, I don't know why they call it pseudo likelihood. And who here understands what is meant by marginal likelihood? And if nobody understands it, it's cool. Basically, in statistics, the concept of marginal, this is directly from the video, which I put at the top of that thing. Basically, when we have two random variables, the marginal probability is the probability of one of those random variables being equal to something, and finding the probability of that. So we're basically, for example, in this case, we're conditioning x being 1, and we're finding its probability considering all possible values of I. And I'd recommend you take a look at this entire video to really see how he sort of does that and defines it. But similarly here, we're taking all possible values of the ground truth label for that data point across all labeling functions. And that's why we can use the marginal likelihood and why it works really, really well in our case. All right. So they do a bunch of math, which they don't lay out here. Maybe there's a proof sketch somewhere else, but they don't have it here. And they find that the gradient of this function right here is this. This alpha minus beta, where this alpha is defined as this and beta is defined as this. And yeah, it's pretty messy. So, but basically what we do is, who understands like sort of how stochastic gradient descent works? Nate, Carson, neural nets? Do you wanna?
Yeah, do you want an explanation?
Yeah.
It's like you take your like model weights, or maybe in this case, like, you know, just in general model parameters, use a loss function to like see how off it was, and then you like use the derivative, like the derivative of the loss function times like some scaling factor. I use that number to kind of adjust like whatever the model parameter is, so that next time you run a prediction, like you'll have a smaller loss value, and having a smaller loss value just translates to being more right. So yeah, kind of like that.
Right. So thanks, Nate. If we have a loss function here, which takes in our weights, so these are our weights, and this is the value of our resulting loss function, we want to find the minimum value, which is what we're trying to do. We're trying to minimize the loss function, which is kind of what we're doing in machine learning. And we set a value of initial weights. You might be wondering, well, why don't we just use calculus and take the derivative and set it to 0? Well, when we have this many dimensions and this many sort of complex equations to work with, that can be, again, very, very computationally expensive. So instead, in practice, we use this algorithm called stochastic gradient descent, where we set initial weights and we calculate the gradient of the cost function at those weights. And then the bigger this gradient is, the bigger we traverse down the loss function. So we basically adjust those weights in the direction of the minimum, which is this direction in this picture. And as that gradient gets smaller and smaller, so you'll notice as we sort of go down, this curve is going to get flatter and flatter, which means our gradient is going to get smaller and smaller, because our gradient is basically the slope. As we do that, we're going to reduce our step size and get, sorry, whoa, what happened there? My apologies. We're going to reduce our step size more and more until we kind of approximate the minimum. We're probably never going to get perfectly to it, but we're going to get pretty close with this algorithm. That's how it kind of works in a nutshell. I recommend everyone check out a video on it to really understand it better. It's a really cool technique, which is used very, very widely. Cool. And that is sort of how they're optimizing this formula right here. We can't find the exact weights which minimize this function, but we can approximate it with SGD. And the reason we do that is because if we tried to do it the brute force method of calculus and taking derivatives and setting them to 0, it would take forever. So this method is much, much faster. And let's see, what did I leave out here? And so basically, yeah, as they've said here, we're sort of optimizing for each labeling function. We're repeating this process. And for those labeling functions, we are selecting the dependencies where the parameters that have a sufficiently large magnitude and adding them to our C. So let's see, let me explain that better. So why don't I just actually, so as I mentioned earlier, this epsilon term, forgive me, I don't understand this 100%, so bear with me. This epsilon term does not just serve as a regularization term, it also serves as the correlation coefficient. So the lower we make it, the more correlations we're going to get. And we're going to identify to put into our C over here. And this is the full algorithm. Why don't I have everybody just take a minute and look at it? And please ask questions if you have them right now. So I'll just kind of go through this algorithm. We start with an empty list represented by the empty set again. And then for each of our labeling functions, we're going to set initial weights similar to what I just showed you when we do that with stochastic gradient descent. And then we have this epoch count parameter where people who've done neural nets know what an epoch is. It's how many times we sort of repeat a process. Excuse me. And then for each of our data points, we're going to look at all the weights in our weight vector, which is our initial weights. And we're going to get that alpha value and that beta value, and then use that to calculate the gradient. And along with our step size, which is a hyperparameter into that algorithm, we're going to get a new value for our weight. And I don't really understand this, to be honest. They did not explain this, why they use sort of this formula right here. For the weight in that initial weight vector, where it's greater than 0, set that value to the max of 0. And this, I really do not understand all of this, how they came up with this, but that's just what they did. And then finally, we have all of these values which are new in our weight vector. And if that value is greater than that threshold epsilon, then we add the corresponding pair of labeling functions to our correlation vector, which is, you can think of basically D here is synonymous with C right over here. And again, we do this across all labeling functions. So I'm guessing that if one labeling function is identified to be correlated with, like say labeling function 1 is identified to be correlated with 7, and if 7 is correlated with 1 later when we do it, when J is 7, I think we just treat them as the same because they're basically the same thing. Does this kind of make sense? It still doesn't make 100% sense to me.
So like in a general sense, is it just like if the correlation is strong enough, then add it to a set? Exactly.
And we, if the weight on that correlation is strong enough, yes.
Oh, yeah.
Yeah, and we do that, we decide that by this hyperparameter, which the authors mentioned right over here is the only one which needs tuning, not any of these other ones, not the step size or the epoch count or this truncation frequency, which I still don't really understand. They didn't explain it at all in this paper. They have sort of these default values for them right over here. So for all of our labeling functions, we're setting an initial vector of weights and modifying them based off of applying stochastic gradient descent to this loss function right here. Yeah, take a second and go through it. Again, none of us need to understand this perfectly. I think it's just kind of cool to see sort of the connection between all the sorts of different processes. It's also really cool to see for me, like how they go from just laying it out in math to actually defining an algorithm for it. Yeah, feel free to ask questions. Or just
Can we talk about, I'm having trouble interpreting what the K times eta n, it's called eta, right? That's the Greek letter.
Which one? Here?
Yeah, yep. So K times eta times epsilon.
Yeah, so they define this parameter truncation frequency K, which, okay, let's see. So they say R, which is right here. So M is our data point. So, or the number of data points we have plus I, which is the specific data point we're on. If that plus I is modulus K is 0. So if that divides, if K can go into that, then do all of this. I don't really understand this part very, very well, to be perfectly honest.
Mm-hmm. No.
What the intuition behind this is.
I guess like
yeah,
one part of it, like the mod K is just like taking every cape sample from the RM plus I. So right.
Every
So it's
Kate
just like
sample.
So like if it mods K,
Oh.
it divides. So it's like taking only some of them and not all of them, probably by like with some interval apart. Like I don't understand what it means in context, but it's probably like they didn't want to use all the data, only
Right.
like every cape piece.
Yeah.
So that's all I got for that.
I think that seems to make sense in some sense. Yeah, it all seems really arbitrary to me. But if it works in practice, it works in practice. So one question I have for you all is, oh my God, it's already 8:45. Are you guys staying like an extra like 20 minutes? I'm sure that's all we'll need to cover everything down here. Okay, thank you. So basically what happens if we reduce this parameter epsilon? What do you guys think will happen if we make it smaller? In terms of how many correlations we'll have.
We'll find, I'm assuming we'll just find a lot more correlations between.
Exactly. And that's exactly what they show in the paper, in fact. Let me go to it. So where is it? It is, yes, here. So the x-axis here is the correlation threshold. Let's just look at one, epsilon. As we make it smaller, we're going to find a bigger number of correlations, which is the dashed line right here. But what they show right over here is there's a certain elbow point where, yes, in some cases, performance in these two cases, for example, performance increases, but not really by much. So what our objective is to find this elbow point of a correlation threshold epsilon, where we sort of balance computational complexity with performance. Because the computational complexity increases as you have more correlations, because this model basically relies on using them. So the bigger this is, the more complex this is. So we want to find that sort of optimal point. Does that make sense to everyone? Cool. All right, so that is how we find C. That was something which I kind of went on a very long quest to find out, because they did not really explain it at all. They basically just said, refer to our process here. So I was like, okay, bet, I'll do it. So yeah.
Wait, sorry.
Yeah, go ahead.
One more thing. So is just I don't know if they talked about this at all, but like it seems like finding the proper threshold epsilon kind of takes a decent amount of it must take like a decent amount of computation, right? So like
Yeah.
does it really like when you factor this algorithm that's supposed to make things faster plus the computation of time of finding epsilon, like is that really less computationally intense than like I don't know running it on a lot like running all the pairwise differences?
That's what they say, and it seems
I guess
to.
okay. I guess that makes sense actually, but I don't know.
Yeah. Yeah. It to me, like here, let's take a look at this.
Oh no, it would totally make sense. Sorry, because if you found every pairwise function, if you did every pair in like an enormous data set, that would be like super quadratic.
Exactly.
runtime
Exactly.
Versus, yeah,
And
my bad.
what they say is that where was it? We can ensure that all these, that for example, our gradient can be computed in polynomial time with this method over here, which is obviously better than quadratic because we're trying all those pairwise labelings. And they also do say that this is the only parameter that requires tuning, which is probably done through grid search. So I think I'm just gonna take their word for it. I don't really need to do a big runtime complexity on this. That would take some time. But I good thought though. Like that's really important to think about. All right. So any more questions on this? I've put this into the notebook at the bottom here if you guys want to take a look if you're interested in. But I just had a blast looking at all this, even though I don't understand it 100%. Even the fact that I understand it in some form kind of boosts my ego a little bit. Like, hey, I understand this. Cool. Any questions? Cool. All right. So, phew. Now we've got our we've encoded sort of our information on propensity, independence and correlations / dependencies. So now let's go to our actual model. So basically once we have C, we obtain 3 vectors for each of these for all of our data points, or excuse me, for all of our labeling functions rather. Or actually, this is actually incorrect. We 2 of them are length n, and the last one is the length of how many ever dependencies we found. Is whatever. I just won't put it right now. It's not in yours anyway. Okay, so we have those 3 vectors, which we're going to put into our model right here, and this represents the concatenation of those 3 vectors. And fuck, I kind of spoiled it because I was supposed to ask you guys what the length of it is. Okay, so in the paper, this is how they define the full model, where you're taking in, again, your ground truth labels, your label matrix, and you're modeling it like this. So like I've said, of phi sub I of lambda, y sub I is the concatenated vector for our 3 vectors from above. Z sub W is a normalizing constant. And kind of similar to what I talked about here with this sort of, with marginal likelihood, that's the exact same way in which we get our weights here without knowing ground truth. We're again testing out all the possible labels. And in this case, we're not just testing out labels as we do here, little y, we're testing out all the possible label vectors, ground truth label vectors, and basically optimizing for W using those vectors. So yeah, I'll just explain that a little bit better. Minimizing the negative log marginal likelihood given our label matrix sounds really fancy, but all the equation is doing is inputting all possible vectors. There are 2 to the n of them, since we have, in our case, in our binary case, we have 2 labels and n labeling functions. And we're putting that into P sub W along with our label matrix and finding the weights which minimize their weighted sum. So basically classic machine learning. So a question which I have for you guys is, what do you think the length of W is? And it's the exact same as the length of this vector right over here, because this is a dot product, which those of you who've taken linear algebra know. Any guesses or any informed guesses on the length of these two?
I would say 2n plus the length of the dependency vector, which
Exactly. The length of C, right? That is exactly right. Let's go to that section in the paper. Yeah, so W is an R2n plus C, exactly the same as phi sub I, because we have two vectors of length n for all of our labeling functions, which is from the propensity and from the accuracy. And then we add it to the vector, which is of length, how many ever of these correlations we find. And that defines this along with this. So great job, Marwan. Does that make sense to everyone? Why? Cool, awesome. So that's that. And so again, finding W prime will take a long time if we do it by brute force, which means again, using calculus and setting the derivative to 0 and finding that out, because this is a very big problem. And in fact, here we're using a vector instead of just the simple labels themselves. So it's kind of even bigger. So now the authors talk about using something called Gibbs sampling along with stochastic gradient descent. And I had a video on Gibbs sampling up here. Did anyone, Serena, did you get a chance to watch that video?
Yeah,
And did it make sense to you fully?
like it makes sense on a micro level, but I don't think I'd be able to figure out how to apply it to this.
Yeah. So this Gibbs sampling is a Monte Carlo method, which basically means a method of sampling from a distribution which is basically hard to sample from. And it's techniques to kind of do that. And so basically, I've said, who besides Serena saw the video? Anyone? Okay, that's totally fine. Basically, we are inputting our ground truth labels, our simulated ground truth labels, and we're using that to get sort of this probability right over here. And that is sort of exactly how Gibbs sampling is designed to run. Let's wait for this ad. Hello, Loki. Right. Whoop. Let's move him out the way. So you can see here, Serena, you probably recognize this from the video. When we have a conditional distribution which we want to sample from, this is when Gibbs sampling works the best. Through this procedure right here, which I won't go through, I'll just have everybody watch the video if you're interested. And that's sort of the beauty of our approach here, because that's exactly what we're sampling from. We're sampling given a simulated ground truth label vector, which could be represented as the conditional right here. What is this? And we can sort of simulate sort of that loss function over here. This one right here specifically. We can simulate, we can simulate values in it, and then we can use stochastic gradient descent to find the minimum. Take a second to gather all of that and ask questions if you have them. Any questions? So basically, the authors talk about in the paper, they talk about using stochastic gradient descent with Gibbs sampling. I I'm not 100% sure where they use SGD specifically and where they use Gibbs sampling, but I would guess we know that they're using Gibbs sampling right over here, or excuse me, stochastic gradient descent right over here. If I were to take an educated guess based on my limited knowledge, I would say that they're using Gibbs sampling to get sort of to kind of estimate that loss function, or excuse me, estimate that this distribution right here, and then taking the loss function with this and using stochastic gradient descent to optimize that loss function, but I'm not 100%.
Wait, why are we minimizing the negative log marginal likelihood?
Because that is the optimal weights, which maximizes the likelihood. So if you've taken a look at the video on maximum likelihood estimation, which I've put here, you'll learn that basically when we're given data and we want to model the likelihood of a parameter given that data, we can use this technique called maximum likelihood estimation, where we want to maximize the likelihood, but that's this exact same thing as minimizing the negative likelihood, which is often easier to do.
So it's like argument of negative log.
Exactly.
Oh, okay.
Exactly. Yeah. And again, I know I didn't explain the sort of Gibbs sampling stuff as well, along with how it's sort of done with SGD, but that's just because I don't really understand it 100%. I'm just making as educated a guess as I can, given my limited knowledge. Does all this sort of make sense to everyone? If not, totally fine. Okay, cool. So once we get our weights, we can get our probabilistic labels by inputting in our label matrix and getting putting in the label. The labeling vector, which is going to be all the positive label which we've designed, because that's what we're trying to get, the probability of those labels. So y is just going to be a bunch of ones, M1 specifically. Did that make sense to everyone? So because we're trying to get the probability that of the positive classes, this whole thing is just going to be ones. And we're going to use those probabilities as our probabilistic training label. Cool. Sorry, guys, almost done. So now that we have those probabilistic labels, now we can train a discriminative model. And so you might be wondering, if we have this labeling function infrastructure set up, why do we even need to train an additional model? And the reason is we want to generalize beyond the information contained in our labeling functions. While they hopefully are robust, and just as a little side bit here, I put the authors found empirically that more labeling functions lead to better performance, which makes sense. While our labeling functions hopefully perform well, they can still lead to the generative model overfitting on the info they contained. So I talked about overfitting a little bit earlier. This is still a problem with our labeling functions here. We don't want to overfit on just the heuristics that our labeling functions contain. So to mitigate this, we train a discriminative model H sub theta, where we optimize for what the authors call the noise-aware variant of the loss. Whatever the loss function of which we use for this model is, we're going to minimize this right over here, which is that noise-aware variant of the loss. So take a second to just look at this formula.
What is this boldface E?
It's expected value.
Okay. And this is it the expected value of the our model with data point I expecting label Y?
Exactly.
And then And is L this what is L?
L
And
is
then
L is whatever loss function we choose for our model.
okay.
So this discriminative model can be any model we want. It can be a neural network, it can be a classifier, doesn't matter. But whatever loss function we choose is what L is. Yeah, it's a little bit complex.
And we're trying to find, is it theta which minimizes this
Exactly.
this
Theta is what the hyperparameters for our model.
oh okay, I see.
Yeah. Yeah, great questions. Anything else on this? I still don't intuitively understand really what this actually means, as a lot of other things in this discussion, but that's what the authors say right over here. And they don't really go into why they have this, but I guess we'll just take the word for it. Okay, cool. And as the author discussed, the more unlabeled data we feed into our full pipeline up here, the better we're gonna generalize. And as they say, the generalization error of our discriminative model decreases with more unlabeled data at the same rate, I think, as a supervised model with a certain proportion of hand-labeled data compared to the unlabeled data we have. So if we have, I think it's, let me go back to the paper and see what it was. They say asymptotic rate, they don't give the actual rate, but there's some ratio between the amount of unlabeled data we have with actual human labeled data, which we could have, where if we have that ratio of unlabeled data, the generalization area of this discrimination model decreases at the same rate as a supervised model with hand labeled data. That's kind of just something the authors put in just to kind of quantify why we sort of do this discriminative model and how much it helps. So, and this makes sense because the more data we have, the more features we will learn from the labeling functions, while also sort of generalizing, excuse me, more beyond the noisy probabilistic labels. Cool, and that's all I had. I know this was kind of a lot. This, honestly, I don't think we really needed to do this for our project. I just thought it would be interesting just because, one, I didn't present, and two, I was kind of very interested in going very deeply into these things. I had a blast doing this. It's really fun reading a paper and at least getting some form of clarity on it, if not 100% clarity. So I had a blast doing this. So I hope you enjoyed this, even if it was super confusing. Any other questions on this? Any questions, important, any questions on any terminology? You guys all had great questions about sort of what this means and what this E over here means. Any questions on those things? Because I imagine you guys will be seeing these a lot more. Okay, awesome. The one thing which I will try to clear up is this right over here. I think this was the part which I understood the least, excuse me, whoa. This was the part which I understood the least, where we use Gibbs sampling and where we use stochastic gradient descent. I think the authors made it pretty clear that in correlation, in finding those out, they use stochastic gradient descent. They don't mention anything about Gibbs sampling, or excuse me, they do here. Let's see. Gibbs sampling to estimate gradients. Oh, wait a minute. Let's see. Learning the parameters of the general model requires Gibbs sampling to estimate, but they've said they use stochastic. Okay, I'll have to look more into this, and I might ask Brian about that specifically, because that's the one thing which I'm having trouble with. Okay, I will stop my share. Would you guys like me to do the same thing with confident learning, or do you guys think this is it? This is good enough?
I think that would be helpful. I think this was pretty helpful.
It was? Oh, I'm very glad. I'm glad. Okay, was there anything which I could have done better, or which was particularly effective in the way I explained it, or in anybody else, the way anybody else talked today?
I think the section where you were explaining like the generalized model and um what was it called? The pseudo likelihood marginalized log, and how like you use sort of just stochastic gradient descent to optimize it. I think that step is something that you explained really well, and you sort of really did well in like describing the intuition behind the model and like why we do those steps.
Cool. And that's obviously credits to Carson and Nate for helping explain some of those concepts. Yeah, we're a team, guys. Okay. Anything which I could have explained better?
This is like unrelated, but I think like what was helpful for me was like explaining the notation and like what that stuff meant, and how like especially how each symbol like corresponded to the stuff that was in the text. Like it sounds pretty simple, but like for me when I'm reading it initially, like I'm like really confused by the equations.
Yeah. Awesome. Cool.
Yeah, I'd like to second that. That's a huge thing.
Okay, cool. Awesome. Thanks for that. This is purely for my own education. I just really like explaining things to people, so this helps. Awesome. Carson, anything?
No, thank you for putting together that presentation. It was really helpful.
Yeah, of course. It's all because you guys did such a good job presenting the other day, to be honest, your papers, and I just wanted to join the party. So awesome. Okay, I've kept you guys way too long. Thank you guys so much for staying on. See everybody on Thursday. Bye, guys.